Hello, welcome to Jorge Does Math. For inquiries, you can email me at jorge.rodriguez@lean6sigma.net. The purpose of our channel is to introduce the students to math, stats, geometry, and physics. If you like our material, don't hesitate to subscribe by hitting the button below. We want to build a community of people that love math, stats, geometry, and physics. So without further ado, let me introduce you to today's content. We're going to talk about integrals using trigonometric substitution. Okay, the integral that I have selected for this video is the square root of 9 minus x squared dx. When you see a structure like this, immediately you should be thinking about trigonometric substitution. There are basically three cases, and we're going to study in this video one of them, particularly case 1. The whole purpose of trigonometric substitution is to get rid of the square root that you see in the integral so that we can simplify it and take it to a more manageable, recognizable type of integral that we can solve easily. Now there are several tricks that we're going to apply through this video, this being the first one, which is the core of the trigonometric substitution. The intention is to be able to use trigonometry so that we can replicate the structure that we see in the integral. To that end, we're going to create a triangle. We're going to call an angle of this triangle here theta. And to be able to create the square root of a squared minus x squared, the first thing that we need to recognize is that the integral, the example that I'm showing you here, actually fits this case, because we can rewrite that function as 3 squared minus x squared, where then a is going to be equal to 3. So how can we then create square root of a squared minus x squared? Well, if we call this side x, and if we call the hypotenuse 3, then by Pythagoras, you're going to be able to see that 3 squared is going to be equal to x squared plus the side that is adjacent square. So substituting here, we're going to have 3 squared minus the adjacent side square is going to be equal, I'm sorry, it's the other way around. 3 squared minus x squared is going to be my adjacent side square. And then if I just want to know what the adjacent is, then that will be the square root of exactly what I have there, 3 squared minus 9 minus x squared. And this is exactly the triangle we're going to use to solve this function. There are two other cases. The case where the x squared minus a squared, we're not going to be dealing with that. In another video, I'm going to leverage that particular case to show you how that will be applied. And then we have the case where you have x squared plus a squared. You can see how, depending on what structure you have, the triangle changes. So let's use this concept to be able to solve this integral. Okay, so now that we know what triangle we're going to use, the next thing that we need to do is to start the transformation of my square root into a trigonometric function. We're going to use another useful concept of trigonometry, which basically states that the sine square of an angle plus the cosine square of an angle is equal to 1. And for this particular function, as we can see here, we have as the adjacent the square root of 9 minus x squared. So that means that we want to bring my integral to the cosine function. So we're going to look into what the cosine square of theta is, and that basically is going to be 1 minus the sine square of theta. Okay, all right, so that is the first trick that I need to see. So you can immediately see that this is starting to take the shape of what is right there in my integral. Now, how can I then make this be similar to what we have there? Well, we need to then call the variable x a trigonometric function, and that's basically going to be x is going to be equal to the sine of theta. But I have a little problem, because if I then square x, then this becomes the square, and that doesn't quite sort of look like the one that I have there, because for me to be able to formulate this, I'm going to have like a 9 here, because you can see that this one, you can sort of rewrite this as 9 minus 9 sine square of theta if I multiply the cosine by a 9 over here. Okay, so if I multiply the cosine by a 9, that is the same as multiplying this times a 9, and then it becomes like that. So how can I then make that jump? Well, what if I then, instead of doing this, I make my x be 3 sine theta. Therefore, if I square now, then this becomes 9 sine square theta. Now, if I take this substitution that I have here and I plug it into my function, which is 9 minus x squared, and then I use that substitution, we're going to see that the square root now becomes 9 minus 9 sine square theta. And I can continue to work on this, because I can then take the square root of 9, which is a common factor between these two, and then 1 minus sine square theta. And immediately you should be able to recognize that that is exactly what we started with. The cosine square of theta is 1 minus sine square theta. So we're going to then rewrite this as the square root of 9 times the square root of the cosine square of theta. Okay, so we have been rewriting our integral so far. Now there is another thing that we need to take care of, which is the dx before we go back to the original integral and be able to substitute everything I'm working here on the side. Now we have defined x as 3 times the sine of the angle theta using the triangle that we have here on the left. So we're going to then derivate that x to be able to find what dx is equal to. So if we take the derivative of x, if we take the derivative of x with respect to theta, we're going to find that this is 3 times the cosine of theta for the differential of theta. Now I know what my integral looks like now that I have all of the functions. So we know that the square root of 9 minus x squared using my substitution is then going to be equal to 3 times the cosine of theta, and now I know that dx is equal also to 3 times the cosine of theta. So I can rewrite my integral basically to be 3 cosine theta times dx, and then dx we know is 3 cosine theta differential of theta. And using a little simplification, we know that 3 times 3, that's 9. We can take that 9 outside of the integral. Then what I have to then solve is the integral of cosine squared theta differential of theta. So we're making progress here in our integral. I have summarized all of the steps that we're taking. So we just said that now the original integral of the square root of 9 minus x squared can be then rewritten in terms of theta as 9 times the integral of the cosine square of theta d theta. Now I need to manipulate what is inside this cosine square of theta by leveraging some trigonometric concepts. So I'm going to use the trigonometric transformation where the cosine square of theta can be rewritten as 1 plus the cosine of 2 theta divided by 2. So by using this transformation now I can simplify my integral tremendously. So I'm going to then write that what I'm trying to solve here is 9 times the integral of 1 plus the cosine of the double angle theta divided by 2 differential of theta. We can see that these two can come to the outside. So my integral then becomes, let me find a little bit of white space here, 9/2 of the integral of 1 plus cosine of 2 theta d theta. Now that we have cleaned up our work here, you can better understand where we are in solving our integral. Now we have a very simple case where we have to use some of the properties of the integral, and then I can break this integral into two components. So taking the work from the 9/2 integral of 1 plus cosine 2 theta, the theta, we're going to break this into 9/2 of the integral of differential theta plus 9/2 of the integral of cosine 2 theta differential theta. And this one is very easy, so we're going to concentrate on this one first, and then we're going to solve everything in one shot, and then we have to take everything back to the variable that we started with, which is basically x. So let's concentrate on the integral of cosine 2 theta the theta. So how do we solve this particular integral? Well, this is the classical example of using substitution. So we're going to create a variable here that I'm going to call v, and that variable I'm going to call it 2 theta. Therefore, the differential of v is going to be 2 times the differential of theta, because the derivative of theta with respect to theta is 1. Now, I don't quite have 2 times the differential of theta on my original integral, but we can use a very simple mathematical trick by taking 1/2 and then multiplying this times 2. So by doing this over here, I have basically done nothing to my integral, and then I can then rewrite this original integral as 1/2 of the integral of cosine v differential v. And we know that this is a very well common integral, which is essentially the sine. So this integral here, I'm going to find some white space in my slide, is going to become 1/2 of the sine of v plus a constant that I'm going to call c prime at this very moment. Now, what I have left to do is to return the substitution, and then I can see that that integral then is going to become 1/2 of the sine of 2 theta plus some prime over here. So I have summarized in the square in red the work that we did to solve the integral of cosine of 2 theta. Now we can proceed, now that we know what the integral of cosine of 2 theta is, we can proceed to solve the other integral that we have pending, which is the integral of the differential of theta, which is primarily just theta. So we're going to take all this work that we have over here, and we're going to start finding the solution of our initial integral. So this is going to become 9/2 of theta plus 9/2. And now we know that the integral of cosine of 2 theta is actually 1/2 of the sine of 2 theta plus some constant prime, and then we're going to actually put plus a constant here since we're solving all of these integrals. So now it's obvious that when I take 9/2 and multiply this times this side c prime and then add it to c, which I'm going to call this c prime prime, that's going to be equal to another constant. So we can simplify our equation now to be 9/2 of theta plus 9/4 of sine 2 theta plus a constant. And this is the actual answer of my integral. Now I have to return all of the transformations I've done so that I can report the answer to this integral in terms of the original variable, which was x. So we have to go back and do that. Now that we have solved the integral, it is time to return everything to the original variable, which was x. So the first thing that we need to do here is to identify what theta is equal to. If you remember, we did a transformation where we call x equal 3 sine of theta. Therefore, if we work with this, we're going to see that x divided by 3 is equal to the sine of theta, and the inverse function of the sine, which is basically the arcsine of x3, then is theta in this particular case. So we know what theta is, and that is given. Now the next thing that we need to do is to identify what the sine of 2 theta actually is, so that I can bring everything back to my original integral. So here I'm going to leverage an interesting property of the sine function. So the sine of 2 theta is equal 2 times sine of theta and cosine of theta. So knowing this and going back to my triangle, if you look at my triangle here, if this is the angle theta over here, okay, then I can identify that the sine is actually the opposite side divided by the hypotenuse. So this sine of theta becomes x divided by 3. And if I look at the cosine, it's actually the adjacent divided by the hypotenuse. Therefore, the cosine of theta is going to become the square root of 9 minus x squared divided by 3. So sine of 2 theta is then equal to 2 times x divided by 3 times the square root of 9 minus x squared divided by 3, which I can simplify to be 2/9 of x times the square root of 9 minus x squared Okay, so we've come a long way. Now we're going to leverage the triangle and continue to change all the variables back to the original x. So in the previous content, we were talking about the fact that we use the trig substitution x equals 3 sine of theta. Therefore, the arcsine of x divided by 3 is theta. So we're going to plug that back into our object over here of 9/2 theta. We're going to get that answer. Now, we're going to use the triangle in this trigonometric property of the sine of the double angle, which basically states that the sine of 2 theta is equal to 2 sine theta cosine theta. And in the triangle, we can see that the sine of theta is x divided by 3, so is the opposite divided by the hypotenuse, and the cosine is the adjacent, which is square root of 9 minus x squared divided by 3. So taking all of these numbers over here and doing our math, we can see that 9/4 of sine of 2 theta, and this 9/4 comes from over here, this area. We can see the 9/4 of 2 sine theta cosine theta becomes this expression, and then after simplifying, we get x multiplied times the square root of 9 minus x squared divided by 2. Now, with all of this information plugging back into this equation over here, we get our final answer for the integral. So the integral of the square root of 9 minus x squared dx is 9/2 of the arcsine of x3 plus x times 9 minus x squared, the square root of that, divided by 2, plus a constant. So everything is summarized here very cleanly. I hope you enjoyed this video. Join and subscribe for more content. And if you like what you saw, please share this video with your peers. This is Jorge Das Math. Thank you.